Please welcome Paul Magder, who graduated from College of Canada as an electronics technologist. Paul worked in manufacturing for 20 years in the electronic industry. He retired as the Director of Operations in 2015. In 2013, Paul co-founded Repair Cafe Toronto and is a fixer servicing small home appliances, electronics, computers, cell phones, and mentoring apprentices. He has created and presented many workshops about repairing and basic electrical and electronics theory. Thank you, Paul.
Thank you. Hi, everybody. Welcome back. Part 2 of the troubleshooting workshop. We are going to have I'm going to do a practical demonstration of a repair, and that people asking to demonstrate as well as talk about it for my previous slide presentation. And then after that, I've got another presentation to talk about common failure mechanisms. So the types of things that you'll come across most commonly, why they fail, and how to fix them. And I also can talk a little bit about some techniques, soldering and crimping techniques, but we'll see how it goes. If anybody has something that they're working on, at the end of the presentation, we can go over it, go through it. So let me know as we're by that point if you want to talk about specific problems. So I'm going to switch over now to my camera here. Can everybody see? Okay. So this is what we're going to fix today. It's an iron, obviously. And the story behind this iron is kind of related to our discussion last week. What happened was a friend of mine had a problem. They said their iron doesn't work, and they gave it to me to look at. So as you may recall, the first thing I always say is replicate the problem. And that's what I did. I plugged in the iron, put water in it, plugged it in, and it worked perfectly. I even took something and ironed some clothes, no problem. So I told my friend, I don't see anything wrong with it. Maybe it was somewhere it was plugged in your house. Anyway, she took it back, tried it again, called me up, it doesn't work. So this actually happened one more time where I got it back. I couldn't find anything wrong with it. I mean, it worked. So finally she said, it works sometimes, but then it stops working. So I said, okay, I'm going to open it up. I hadn't done anything except actually try it. So now I'm going to follow through with what I told her I do. I'm going to open it up and see if we can find there's a problem. I did plug it in when I got it again. It was working again, but I don't want to do that now because it'll be too hot for me to work on. So you'll have to take my word for it. So what we're going to do, first of all, is one of the things about electricity is you got to be careful about short circuits. So usually what I do when I get something that I'm not sure about is I'll test the actual plug to make sure that it's not shorting, which means that these two are connected together. So I'll just demonstrate that right now. It's basically, we're going to use my ohm meter here. We're going to set it to continuity, which on many meters, I don't know if you can see this right here, there's a little symbol of a speaker, which is actually representing a beep. So when you have a good circuit where there's a full connection, nothing broken, then you'll get a beep, which means you've got a good circuit. Can you hear that? Also, it goes, if you see the number, it's going close to 0, which means there's no resistance. So the continuity measurement is actually a resistance measurement. And what your meter does is it puts a little bit of current to the circuit and sees if it can measure a voltage. So now in this case, we don't want to hear a beep. We do not want these two parts to be connected. So I'm going to clip my meter onto both halves of this plug and hope there's no beep. Oh, there's a beep. Oh, no beep. Oh, so that's interesting. Let me try that again. Maybe I accidentally touched these two together. I'm going to wiggle this around a bit. Oh, so there you see there's something going on in this wire that's causing the two to touch, which is actually very dangerous, and especially, I mean, normally it would blow your fuse in your breaker in your house if that were. So it's a good thing that I'm going to be fixing this. So in order to find out the problem with the wire, we got to find out where is it breaking? Where is there a connection going on? It could be in the plug itself, or it could be anywhere along this wire. So what I'm going to do is I'm going to open up the iron and find the other side of this cord and then measure between the two ends of the prongs. And that way we can see if there's a problem between where this connects to the iron and where that connects. It could be in the iron or it could be in the cord. So, oops. Now, remember I was talking about ways of preventing people from opening up things. Can you see that the head of that screw? That's a triangle shape. It only has 3 prongs, which is very unusual. Most screws that people use in manufacturing are Phillips with the 4-pointed star, or slot screwdriver, or rarely they use Robertson, which is the square one. So most people do not have this kind of screwdriver. Luckily, I have a kit here with multiple screws. I think I showed a picture of it before, but this is all kinds of different screwdrivers in here. I don't know if it's...
Yeah, it's quite visible. Thank you.
You can see here we have the triangle shape, different sizes. So I'm going to open my screwdriver set, and I already found this. Where is it? You can see it's a 3-pronged screw head.
Paul,
So
a question about safety. Are you, I know you covered this in part 1.
Right.
Should you be wearing gloves or other kind of safety kind of gear at this point in time when you're working with any electrical appliances?
At this point, because it's a very straightforward opening, there's no chemicals involved. It's not hot. We haven't heated it up. I don't need any safety equipment yet. One thing, of course, this cannot be plugged in. That is the most important point with opening this particular item. So you need to make sure that you're not plugged in at all. So now I'm going to open it up. And I have back here an ice cube tray where I'm keeping my screws. So if I'm going to get any more screws, I'll be keeping them in order. In this particular case, there's only one screw. It has a kind of a locking system, so it's popping off at the back here. And the other thing it has, which is a common mechanism in a lot of electrical items, is this what's called strain relief. So here we have a bracket that's holding the wire, so the wire cannot be pulled. If this is screwed in, I can't be pulling it. Here you have your connections to the heating elements. So it's a very simple circuit. there's a switch here. So now we can kind of go through. What I should have done was the block diagram. You've got your power cord. You have your connection, the wire connection there. Here you have your switch. And then you have a heating element inside. So it's a very simple machine. A lot of irons are more complicated. They have lights. This has no light. They have different kinds of mechanical ways of spraying the water. This is a very, very basic iron. Just has one switch, a heat control. So now I've got access to the terminals. You see those two terminals there. I'm going to connect. And in fact, there's no way this can be plugged in, because what we're going to do is connect one side of this to the corresponding other side in the iron. And just hang this over here. So now what we want to know is there a direct connection between where I clipped on here on the iron here and one of these at the other end of the wire. Now, I don't know if you probably can't see this, but normally the wire itself has a labeling system to indicate which side is the ground or neutral, which you notice this is called a polarized plug because it's got different shapes. The fatter one is always the ground or neutral, which is the return, the current coming back through the circuit. The thinner one is line, called line, and that one is where the current's flowing into the circuit. And in this case, you can actually, should be able to see this. There's a gray line, if you can. Well, see the printing? The printing is only on one side. There's no printing on this side, but on this side there's printing. So the printing side, which actually has a gray line, is the neutral. So I can connect and see, I know where to connect on the other side. So here, you can see the printing. So I can follow the printing and then go to clip on to the, so there we have a connection. You hear the beep? Now what I want to do is wiggle the wire around because we had a problem before with that coming on and off. So I'm trying to see if there's any bad connection here. And nothing. It seems to be okay. All right, so now I'm going to try the other side. See that? It's beeping on and off because there's a bad, and it seems to be, there's a bad connection in here. But I'm going to, I just put that somewhere where it won't move while I wiggle the rest of the wire. Well, it's definitely at the plug here. I'm trying to keep the connection while I wiggle around. So in my experience, the bad connection is right here at the where the goes into the plug. And this is a common failure mechanism because this moves around. In fact, there's a little piece of rubber they call, it's a flexible part that's supposed to help prevent that from happening, but generally this is actually broken off. So I'm going to try fixing this plug and then we'll retest it again. So let me just get some more tools.
Paul, while you're going through there, I know there's a question here about a toaster oven, but the fan does not work. So I know you mentioned about different kinds of electrical appliances, right?
Yeah.
So this one here, how does this toaster oven differ from this kind of like the iron? Does it
Okay, a toaster oven, is it a convection fan that it has a convection fan? Is that what fan they're talking about? It must be. So again, that's got a few potential problems. So you have to start, obviously, if the toaster oven is working, but the fan is not working, then there's power getting to the toaster oven. So probably there's not a problem with your power connection. But so the next challenge is to open up the toaster oven. Usually it's all the circuitry is on one side only. And that's the side with all the controls. And often it's pretty straightforward. You can either take the whole case off or just the side comes off. And then the next thing would be to look at the connection between the fan and where the power is coming in to see if perhaps you've got a broken connection. So it's still a matter of looking at different connectors. It's a breaking, because there's a lot of heat and sometimes moisture from, cooking, you can actually get wire connections that will overheat and break, or maybe from the moisture they'll build up some carbon. So that would be my first thing, is to open it up and follow the wiring and see where the fan is connected to the power. And then from there, if that's not a problem, then you might have to look at the actual fan motor itself. And it was where you would use the multimeter to check the motor. And we can talk about motors a bit later. So now I'm going to replace the cord. And one thing you have to do when you replace a component like this is to make sure that you're going to replace it with an equivalent rated item. So what we need to do here is look at how much current this plug can handle. So you look at the iron itself. I'll disconnect this. Most all electric or electronic appliances or devices, they always tell you what the wattage rating is on the item. So I probably won't be able to see it here, but according to this is a 1200 watt iron. So it's written on the back, it's printed in the plastic here. You probably can't read it, but it says 1200 watts. So 1200 watts And I'm not sure I gave you this formula. Someone was saying that, you know, the electrical stuff was a bit, the, you know, the Ohm's law was maybe a bit too in depth, but actually here's an example. It's not Ohm's law, but it's a simple formula that power, which is what wattage measures, is equal to voltage times current. And what we want to know is how much current, electrical current, is this iron using so that this plug can handle that amount of current. Now this plug itself does not have any rating on it, but I know that it's 1200 watts and we know we use 120 volts. So what do you get when you divide 1200 by 120? Can anybody tell me?
After twining, I think Bhavya said.
1200 divided by 120.
Oh, 10. Somebody said, sorry, 10.
10, exactly. So the maximum amount of current that this iron can, 10 amps. That's what it was designed probably to handle more, but they usually put the rating even lower to make sure that it can never be too much current flowing through here. Now I have a replacement plug here from the hardware store, from Home Hardware. It's the same idea. It's a 2-prong. You don't need the 3-prong grounded plug because you've only got 2 wires. On this side, it has the electrical rating, which you may not be able to see. This is a 15 amp plug. It's rated for 15 amps. So therefore, this plug is good for this iron. It's overrated. So when you're looking at amps, you want to make sure that whatever you're using is equal to or above the rating of your item. So we have a good plug here. We can use it. So this is the plug. I'm going to simply cut off this. And I know that and this plug here is not actually polarized. Well, it's slightly polarized. So we know the silver part is the part that's neutral, and the gold part or brass part is line. So the equivalent to this would be the fat one here goes to the silver one. And we know that the printed side of the wire is going to the neutral or the fat one. So I'm now going to cut off this. I'm assuming that the break is here, so I'm going to cut off this cable and put it aside. And now I'm going to reconnect to this plug. So I have to split the 2 wires. And then I'm going to just open up my plug here to see how it's actually, how to connect. It's got some little tabs that hold the rubber around.
So there's some dialogue here about is the formula watts over volts for amps?
It's power, which is watts, equals current, which is amps times voltage. So watts equals amps times voltage.
Okay.
Yes. All right, so now I've taken out my prongs and I see that it's a simple screw on. So the wires go in here and they're just tightened up. Now, one of the big mistakes I always make is I forget this has to go on before I screw it together. Otherwise, you can't slide it on. I can't tell you how many times I've forgotten to put the cover on first, and then I have to undo everything and redo it. So you just push the wire through here, and you slide that out of the way for now. Then I have some wire strippers. So these are for stripping off the insulation. And you want to give yourself enough wire to wrap around the screw, and so that you can tighten it. So I'm going to strip off the wire. Now I like what that crimp wire stripper does is it pinches the insulation without cutting the copper wire. And I like to pinch it and then twist. So I get my wires already pre-twisted, because usually if it's a very flexible wire, most wires, they're stranded. So if the strands start coming all apart, it's a mess. And now I'm going to do the same with the second one. And you'll notice these are not color coded, so I'm going by the insulation here, the indicator, which is that gray line. So the gray line will go, now I gotta do this so you can see it. The gray line goes with the silver connector. I'm just wrapping it around nicely. Take my screwdriver. Oh, and another thing, trick about when you're doing a screw-on terminal, always wrap the wire in the direction that you're tightening. So righty-tighty, lefty-loosey, right? Most screws tighten as you turn them clockwise or to the right. So wrap the wire around from in the same direction. So that way, when you're tightening it, it'll turn the wire tighter and tighter. It won't it'll keep pulling it onto the screw. And there you have a nice, you can't even see the wire. It's nicely buried behind the screw. So again, I'm putting my wire, I'm putting it around this way. And then I'm turning, tightening. And there we go. We have a nice connection. And that's as straightforward. You got your slide up now. And this particular type of plug has little notches that fit in these holes. So it just slips over. And make sure that you get it all the way down so that it's locked in, so that you can't get it off. It won't come off when it's being used. This is a flexible rubber cover. Oh, sorry. Okay. So there you go. Now I'm just going to show you there's other types of there's other types of plugs that you can buy. This is a 3-prong, so this would have a ground. And most of the time, the ground wire is green. Green is the color of ground in almost all electrical systems. And in this case, it's got a silver for neutral, gold for line. So the neutral is like the return. And in this case, if you have a separate ground, you don't call this ground now. This is neutral. And I don't know if I talked about this. There's the reason you have a separate ground is for higher voltages or more current type circuits. You don't want the ground to be changing. Sometimes the ground can move around actually electrically, change. So this way it's tied to earth. This will be earth ground. It'll always be grounded to something that will not move electrically. And it has a one screw. It unscrews, you pull this out, put the wire through. There's screw-on terminals, push it back and screw it in. This one is an older fashioned type. It has 3 screws holding the inside, and then you push up the wire through there. So there's different types of plugs that you can use.
Paul, is
And
it
you can also
applicable to any plugs that whether it's the computer charger or phone charger? Is that pretty much what you just did? If it wasn't.
Yeah, they're all used for all kinds of electrical equipment. It's more about the rating. So these, for instance, these are also 15 amp. They have it says right on here, 15 amps. And it's more about the size of the size of the metal. The metal, physical size of metal is what manages the amount of current that can flow. So now I'm ready to retest again. I've got my plug, and as I recall, it was the line that was the problem. So now I'm gonna, and also it was even when they were both plugged together. So I'm going to connect here. You can hear the beep. It's not changing. It's on and it's on. I'm going to do the other side. All right. So there's one other thing I made. I may have misled you a little bit. In this case, when I connect these two together, they're actually going to beep. And the reason is that this iron is so simple that the connections from here are going directly to the heating element. And a heating element is just a wire. It's a bare wire. Sorry, not a bare wire. It's a thick wire that when you put current through, it heats up. And so to the meter, it looks like a complete circuit. It doesn't look like there's anything preventing these two prongs from being connected. But the difference here is, I think, you have a little resistance. You see that? It's not much. It's 13 ohms. But if it was a short circuit, it would be 0, almost 0, like this. See, that's close to 0. So in this case, there is a heating element, even though it's a bare wire, a plain wire, still has some resistance. So it's showing 12.8 ohms. So there are times when you test these, they will be seem like a short circuit. So you have to look at your meter and see what you're measuring. And also, if you understand what the circuit looks like, then you'll be able to explain it. So that's basically it. I'm not going to plug it in because I don't want to heat it up right now. But as far as I'm concerned, we've found the problem, and it explains my friend's problem because it was broken here. So when she plugged it in, maybe her wire was hanging down from the wall, whereas mine was in a different position, or maybe I wasn't moving the wire as much. But she was right. There's definitely a problem, and now I'm convinced that it's fixed. Okay? So now I'm going to go on to back to the presentation, unless there's something else someone wants me to show them.
There's also questions about, I know you're going to other ones, about earphones too, by the way, Paul. Both Manoj and Tony had mentioned that they were having issues where there's static noise or there's noise when they're listening to songs with their computer, or sometimes not working at all.
Okay, well, we're going to talk about that in the presentation. That's one of the first things we're going to talk about, okay? Anything else?
No, that and the toaster oven fan. I think you said motors that you're going to get into.
Yeah. Okay. So I'm going to, whoa, share my screen now. It's a strange color. And I think I'm just going to start right here because we already talked about it. My computer's a little slow. Can you see that?
Yes. You just need to make it bigger.
Come on. There we go. Okay, so we'll just go right to it. The idea of this presentation is to talk about common failures and show you what we can do to fix them and how to go about fixing them. And we talked about it already with this example, but we'll do other types of things. So there's the three most common failure mechanisms in electrical equipment: broken wires or loose connections, which is what we just dealt with, blown fuses, and broken or dirty switches. So that is the most common thing. And if you think about the block diagram again that we talked about, the first part of the block diagram is always the wire connection, the connection connecting electricity to your item. The fuse is normally the next connection. It depends on what the design is and how much current is flowing. And there are other kinds of fuses besides power fuses, is what the picture of fuse I'm talking about. We'll talk about those. And then the next thing is the switch. So the switch is controlling the flow of current. So basically your main connection, your electrical protection, and then your means of control. Those are the three common things that fail in a circuit. And they are all kinds of different configurations that we can look at. So the first one will be broken wire or bad connection. And here you can see the example of that we just fixed, where the break is right where the item plugs into the wall. And that is actually the most dangerous type of problem. And you'll know everybody is told over and over again, never unplug your item by pulling on the wire. Grab the plug and take it out of the wall. Do not yank on the wire. Electrical wires are not meant to be mechanical. They're not mechanically built to hold weight or take any kind of pressure. A wire is not a rope or a cable. A wire is an electrical conductor. So you have to be very careful with them. And I know people, take them for granted, but if those two wires were to short together in a way other than the example I gave you, if that wire shorted and there was zero resistance, you would blow a fuse if you're lucky, and if you're not lucky, you would start a fire. So it's a very, very dangerous thing to fool around with. The next common type of break is what the question was about: headphones. This is a USB connector, but it's a very similar type of cable. They're very, very fine wires that run between your headphones and your connection to your whatever sound you're plugging into, your computer, your phone. The wires inside are very, very thin. And I think you can see here, there's multiple wires in here. A USB connector, which is similar to an audio plug, has at least 4 wires, sometimes 6. And yet it's a very small overall diameter. So in there are very fine wires, and flexing, they try many ways to prevent the wires from breaking, but it's almost inevitable, especially with headphones, that the wire is going to break at some point. And normally that's what's causing your static, because when a wire breaks inside insulation, often it doesn't actually separate. It just breaks, but it's able, if it touches, the 2 broken ends touch, you'll get something going on. So if you're listening to music, you'll get sound, but then if it flexes, you'll lose the sound. And then when you flex it again, you'll get it back. Or worse, you'll get a lot of interference. Sometimes there'll be more than one wire broken, and they'll be cross connecting, and you'll start getting a lot of noise and static. So the trick about that is finding out where the break is. In these 2 cases, it's obvious, but sometimes, like I said, the wire inside will break, and yet it's outside, it looks fine. It looks like there's no problem. And it's because the wires are very thin, and like any metal, when you flex it back and forth multiple times, it'll create a break. The metal will weaken and separate. And so you have to find the location of the break, which is the tricky part. So here's an example of a screw down terminals, which I showed you on that plug. Bigger types of equipment with more current tend to have heavier duty connections. So this could be from a kettle or maybe a toaster oven, where there's actually a screw down terminal, and they're nice because it's fairly easy to replace. What happens is sometimes you get corrosion, or if it's not tight enough, you'll get sparking, and then there'll be carbon buildup, which will prevent current flow. And also, you see how they're designed to prevent the wire from flexing. This is called the strain relief, and it's screwed down to keep these 2 wires, which seem to be coming in from the power cord, from being pulled. When you pull on this wire outside, you're not pulling on these 2 wires on the inside. It's held down by this strain relief here. Now, unfortunately, strain relief tends to pinch the wire to prevent this from pulling, but after a while, sometimes you'll actually get your wire breaking right here. And then finally, you've got soldered connections, which are, you have to know how to solder and desolder in order to replace them. They are the most safest connection, because it's very difficult for them to come apart. There's rarely any corrosion. So normally it would be a kind of situation where you've got too much flexing going on here. It'll break here or at some other point. This is a terrible soldering job. You can see that these strands are all over the place. You're going to have a short circuit here at some point. But normally you've got a hole in the circuit board, and the wires go nicely through the hole, and then you solder the hole up, to connect it. And we can talk about soldering if we have time later on. So those are the kinds of problems that you have. Now with the headphones, normally your break is right at the connector. So this, instead of USB, you'll have an audio plug. And it could have 3 or 4 rings on your audio connector. Sorry, I don't have a picture of one. But if you look at your headphone connector that goes into your phone, it's the same type of thing. It's usually got some kind of strain relief here. but likely it's broken right at this point. And if you wiggle, yeah, there you go. If you wiggle that around, you should get something going on with the sound. Sometimes it's one side's only working. You only got your left and the right's not working. If you wiggle it around, you might be able to hear the sound coming in and out. And that's really how you find the location of the break. It's rarely in the headphones themselves. They're very well designed. The speakers in earbuds and headphones are very reliable. Unless you've got, sometimes if you have a big, set of headphones like earmuff type, and you've got a heavy wire going into them, yeah, like that, then you'll get a break. You might get a break at where it's going into the headphones. But 90% of the time, this is where you'll find the problem. Unfortunately, it's not easy to replace because you have to be able to, you can buy connectors very easily. Hold on a second. Sorry about that. Yeah. You can buy connectors. I'll just switch for a second to the camera. And you can buy them at electronics stores. There's a couple of places. There's the best place to buy electronic equipment is a store called Sayel. Someone was asking, where do you buy stuff? Sayel is a electronic shop. So here is a connector. It has 3 rings. So that's for your headphones that do not have a microphone or a volume control. They just go straight from your phone to the headphones or from your sound source. And then you have, if you have a microphone or source of or a volume control, then you'll have 4 rings. So each one of those rings represents either, normally this is the left, the top one is your left earphone, the next one is your right earphone, the next one is for the microphone, and then the bottom one is for ground. And these are nice because they're designed to be replaced. So you see the hole there? You put your wire through the hole and you solder it. But there are all kinds of videos on YouTube showing you how to do this, like how to actually connect the connector. And you need some kind of tools that will hold this while you're soldering it. And there's some other tricks around the wiring itself, but it's definitely possible. And the more you do it, the better you get at it. So if you have some old earbuds around that you don't that don't work, or someone cut off one end of the earbuds or something, you could try it at home. Try it and learn how to do it, because it's such a common problem. And
Paul, if you can find some of those YouTube that you find are really good, can you send it to me and I will then forward it for the participants?
Sure.
That would be great. And there's also just a comment here about that was asked about, is it good to, because of the strain, as you mentioned, for causing a lot of these breakages. The question was whether is it bad to put twist tie wires in the same position for a long time to get them organized so they don't get tangled on the floor? And I think there's also a comment that to pull the wires and bend them and the plugs has to stay straight, but that this causes abnormal curve and damaging. So that maybe, you know, what ways can you what ways can you do it so that the strain isn't there for that plug?
Well, the thing about wires is they only break from being flexed. So if you can find a way of holding the, you know, like some people will loop this around and then use a wire tie or some mechanism to keep this part from flexing all the time. But the trouble is what happens is it kind of goes down the line. So wherever you stop your, you know, it'll flex over here, it'll flex farther down. It's just more a matter of handling. Do not ever pull it out of your phone by the wire. Don't like fling them around, like, you know, I mean, I know it's hard, but it's about handling, because it's really difficult to prevent, you know, a foolproof method of preventing the wires from breaking. It's more about when you pull out of your computer or phone, you grab it by the connector, then you nicely, you know, bundle up your wire, your headphone, keep it in a case, even earbuds. I have a pair of Bluetooth earbuds that are connected by wire to each other. And I'm just scared because it's if you hang one by, you know, hold one earbud, the other one's dangling down. So I'm always holding them both together, and I have a case, I put them in the case. It's really about, you know, using it properly. And people, I mean, it's hard not to forget about it sometimes. And sometimes it's unavoidable, you know, you're in a rush, you're getting off the bus or something. Like you can't be perfect, but just being aware of it will make a big difference.
Good. The other thing in terms of, other than seeing that it's obviously in the photos that you've shown, bad connections or breakage, is turning yellow, the cable turning yellow, an indication that's overheating in the wires? Or, you know, what other kind of indicators would you have?
Yeah, definitely. Well, if you see discoloration, you can actually, you know, grab onto the wire and feel it hot. If a wire is hot, there's something wrong. I mean, I know that, for instance, when you're charging up your computer or some other device, sometimes the block that's the power adapter will get warm. And really it shouldn't, because heat is bad for electrical equipment. So if it is, it means probably that it's underrated. There's not enough current supplied by that power adapter. And I would get another one with a bigger block, like more, and you look at the ratings and look at the current rating. They always have a current rating on adapters that plug in to charge things. And so if it's getting warm, heat it up. If it's a wire warming up, again, you know, sometimes things are poorly designed. I know that I've had toasters or toaster ovens where I notice the wire gets warm. It's basically a poorly designed piece of equipment. If it's turning yellow or brown, it's not good. And I would, if it was me and if it was an older piece of equipment, I would open it up and replace the cord, get a bigger power cord, a bigger plug. Look at the rating. I know, you know, if it's something that's fairly new, then I would, if it's under warranty, take it back. Tell them this shouldn't be heating up, but it's not good.
Thank you. And in general, are these ones that would you try replacing it yourself for the ones that are the headphones, especially as you said, it's very common? Or is that something that you kind of give away?
it depends how much money you've spent on your headphone. You can buy, you know, earbuds for 10 bucks. And they won't last. I don't, my ear hearing is not great, so I'm not too particular about the quality of sound, but if you are, then you're probably, I know there's really expensive earbuds like those wireless ones, and I forget the brand name of the Beat ones, the Beat headphones can be really expensive. So it's worth fixing in that case, trying. One thing, if you're buying those fancy headphones, some of them have the connection to the headphone is a plug-in connection as opposed to just a wire coming out. So you've got a plug at each end. One plugs into the headphones and one plugs into your source. That's the best kind because then you can just replace that wire. You know, that'd be, if you're going to spend a lot of money, get a kind where you can plug the cable into the headphones. All right, so just a reminder, we've said it many times, you never work with a plug, with power plugged in. And of course, we're talking about power connections. That's why I need to remind you. And, you know, it's really easy to forget to unplug things or plug things in. I've done it myself many times. So you've got to always be looking and checking, even though you know it seems obvious. Make sure that there's no power connected to something you're working on. So how do you fix broken wires? Well, we've talked about, this is the soldering method here, and that's what you would use with headphones. I showed you those little holes. Instead of connecting two wires, you put it's like a circuit board with a hole in it. You put the wire in the hole and solder it together. If you do a solder joint like this, this is actually not a good way to connect things. And I have a explanation because this is using the solder connection as a mechanical connection. So what I do is I make some loops so that there's actually a strong mechanical connection, and then I will tape this up or put sheet shrink over it and tighten everything around. There's usually two wires, but we can talk about it a little bit more in detail when we do the soldering. The screw down terminals are nice. This is a different kind of terminal where it's a plug, and for electrical large, you know, wiring type house wiring, or even some larger appliances use Moretz. Moretz are to use when you don't have to solder. But what I often do is in a box like this, it's okay because they're not going to move around once you cover the box. But sometimes there may be some movement. And what I do is I actually put electrical tape around them after I've put the Moretz on to make sure that they can't untwist. And then there's the crimp type of connection, which is, this is one example. And again, I can show you that if we get to the crimping. You need a crimp tool for that. So if you have a screw down or Moretz, it's not a tool intensive type of connection. If you're replacing a plug like we just did, then you just need a screwdriver. But when you get to sometimes connecting things on the inside of the equipment, you may have to use crimps or soldering. And then I was showing you, you saw on that wire that it had an indicator by putting on one side. So all cables have minimum two wires. And in this case, a very common way of indicating the difference is a ribbing. So you'll find that one side has a rough texture and one has a smooth texture. The smooth is always the hot or the gold connector. It's the main input current coming in. And then the ribbed is the neutral or return or ground. that's coming back out again. So you can, if you remember that, because you're going to be disconnecting things and then forget, oh, what goes where. And this way they help you remember that. And this is just another example of a plug, the way we did the other one. Okay, fuses. So there's all kinds of fuses. And what we come across in our house is the breaker box, which is a resettable fuse. This is the old style fuse. Resettable fuses are great because you don't have to keep any around. The only thing you have to watch out for is that they don't keep tripping. So if a resettable fuse trips a lot, what happens is you'll get burning on the contacts. Electricity wants to always flow once it's flowing. And when you separate two connectors, the electrons will keep trying to jump across the open space. That's what lightning is basically. It's a huge amount of voltage pushing electrons across air. So what happens when that happens, that does that, is it burns the contact. So eventually you'll never get the switch to stay on. So if you keep tripping the same breaker, then there's something wrong. You have to look at it. Then you have very tiny little fuses like these, which are mounted on circuit boards. They're soldered in. I just found one. Somebody gave me a hand immersion blender the other day, and it had one of these on the circuit board. So obviously the person overloaded their, they were trying to do something really thick, and it just took too much current for the motor to work, and it blew a fuse. But that fuse was not meant to be replaced. Obviously, they don't expect you to open it up and replace it. So that would have been garbage. Many fuses are designed to be replaced. This is from another type of breaker box. This is from a car. The glass one I showed you before, it usually sits in a little clips that hold it in place. And the idea of a fuse is it's protection, and the protection is meant to blow so that nothing else blows, nothing else fails, just the fuse. And it should be designed to be replaced. So unfortunately, there are some manufacturers that don't want you to replace the fuse. They want you to throw it out. So the thing about replacing fuses is you have to match, again, it's the same as the plug. You have to match the current rating and the voltage rating with what was in there. And most fuses are labeled. It's very hard to see here, but these fuses are labeled right here, and this is what it says on the side. So the main thing here is the current rating and the voltage rating. Now, the voltage is often rated for 250 volts, which is just so that it covers all parts of the world, because some countries use 250 or 240 and some use 120 or 100. We say 100 to 120. And that does affect the rating of the current. So if what you want to do is match whatever was in the item. So you see here, it actually has the label right on the circuit board for this rating. It's 1.6 amps, 250 volts, and see the clips. So this was designed, very nice design. Pop it out. They even tell you the rating. You can get these fuses. There are places like I was telling you, this Sayal, S-A-Y-A-L. They have shops all around the city, not in Toronto. There's one on Victoria Park, just south of Steeles. And they have all kinds of fuses and all kinds of electronic and electrical equipment. There are other places too, but that's the easiest one to get to. There's a breaker here that you can replace them fairly easily. You just have to, the wires get connected here. This is the rating, 15 amps. And that's a common, most houses have 15 or 20 amp service. And the thing about, what was I going to say about that? Oh yeah, so, oh yeah, of course, make sure when you, if you ever replace this breaker in a breaker box, there's another connection coming, another box that comes between the breaker box and the power outside, and there's a big switch on it. And you got to turn off the power to your whole house in order to replace these. This is just an example of a very large fuse. So that would be the kind of fuse in that box, maybe that your whole house connection has. It's a 500 volt, 400 amp fuse. They're used for, you know, big machinery too. And this is another kind of fuse that you'll come across quite a lot, especially in things with heat. And they're called thermal fuses. So not only do they have a current rating, which you can sort of see here, it's 250 volts, 10 amps. They have a temperature rating, 94 degrees Celsius. So this will blow if there's too much current and if there's too much heat. And they're very common in motors. They actually put them right inside the motor winding, because if your motor overheats, it can catch on fire. So they put these in to prevent that from happening. And there's just different sizes. These have different temperature ratings. Now these ones here are also thermal fuses, or they call them thermal switches. And they are very common in toaster ovens, in microwaves, and in anything that hair dryers, for instance. I think I have some pictures. Okay, this one here, this is some kind of heating chamber, and what they do is they put the metal face right here touching on a metal surface that's heated up. And if it gets over, I think in this case, it's 160 degrees Celsius, it'll blow. So they are actually touching right onto a metal facing. This one actually has a switch, which means it's resettable, but mostly they're not. Here's the example of the thermal fuses. There's a square one, a lower current one. Here's one 5 amp, 150. Now, this is very advanced repair, but you can do it. I mean, if the motor's blown, it's blown. You're not going to be able to fix it anyway, so it doesn't hurt to give it a try. You have to completely take the whole motor apart. Motors are made of rotating part and a stationary part. So this is the stationary or stator part. It's a ring of iron and copper, and it creates an electromagnetic field. Your rotor sits inside, and that's what spins. And it's also an iron, made of iron and copper, and it also creates a magnetic field. And what happens is the current flowing through these wires creates a magnetic field, which is opposite polarity to the one in the rotor. And so the positive poles push each other away, and that's how it turns. It's much more complicated than that, but the idea is you've got two magnetic fields repelling each other. All motors work that way. So if you do take the more advanced workshop that we're offering, we'll go into much more detail about how motors work and how they're designed. So that's thermal switches, thermal fuses, sorry.
We have 10 minutes left, Paul.
Yeah. All right, so never bypass a fuse. The fuses are there for a reason. And if you try and bypass a fuse, in other words, just put a wire across it, you're going to cause a very dangerous situation. like I said, if the fuse doesn't blow, something else is going to go, and it could start a fire. It could be a short that hurts somebody electrically. You never bypass any kind of safety mechanism in any equipment. And this is just, again, reminding you about the dangers of 120 volts. Okay, quickly, just switches are pretty simple things. All they do is close the circuit. So here is a simple switch. It just, when you make the contact there, current flows. When you disconnect it, current stops flowing. But that simple concept can be create all kinds of different ways of doing it. There's multiple types of switches. You've got a push button switch, a toggle switch, a slide switch, a reed switch, a micro switch. They have lights indicating power. Some do, some don't. Push button ones can be, you just push it once and it pops up, or it pushes down and stays down, and you push it again and it comes back up. And so there's all kinds of different switches. The same thing, they're mechanical. There's movement, there's current. Eventually it could break. So what's breaking is the contacts inside the switch. This contact here may burn after a while, or this could break, this constant flexing, moving up and down. And once you have a break, normally switches are, when they fail open, meaning there's no more, you can no longer make a connection. A switch is either open or closed. And so when someone says it failed closed, it means somehow it got burnt at just the point where it was closing and it melted together. This has happened. So it can never open again. But normally they fail. And then this is just what there are different combinations. You can have switches with multiple switching, all different kinds of things. And then you've got electromagnetic switches, which you create a magnet and it pulls the connection down. And that's often used with relays. Let's see. Yeah, relays here it's a way of using a low voltage to switch a high voltage, or a high voltage to switch a low voltage. So you can use 120 volts here, but this circuit's only using 5 volts. You can't use 120 volts here. So you need something that doesn't connect, but yet switches. So that's what they call relays and solenoids. There's a variety of type of electromagnetic switches. Now, I just wanted to show this one. This is from a keypad. So it could be a remote or something where you have, those soft rubber type of switch, push button keys. And what it is you've got a circuit board here. You've got 2 pieces of copper tracing, which is like a wire. And then you've got a button, and it has either a piece of copper or sometimes it's carbon, semiconducting carbon. And when you push down, it connects these 2 together. So what happens when remotes, it's the most common problem. Your hands are oily. You can't avoid it. Everybody has oily hands. And what happens is the oil and dirt eventually work their way under the keypad, and they get in between here and here, and then the button doesn't work, the push button. So what you do, you can take apart this, your remote. Usually this part is like a rubber overlay that just comes off. Clean the connection here, clean the connection on the rubber overlay. It has little dots, and you should be good to go. So the big thing about switches is dirty contacts, broken contacts. Again, when you replace a switch, always match the rating. 5 amps, 250 volts. 3 amps, 250 volts. So make sure that you get the right, it's not just the configuration of the switch. This is a micro switch, but you got to not only find the right switch, but you have to find the correct rating for the switch.
Paul, a good question here. What do you use to clean it when you say about cleaning those connections?
You can use alcohol. Alcohol is the best thing for cleaning these contacts, electrical contacts.
Right. So you would
probably use sorry?
You'd probably use a Q-tip with the rubbing alcohol or whatever, and then.
Exactly. There is a thing called contact cleaner you can buy. It's more for heavier duty, like these kind of connections. If they're burnt, you can clean the carbon off. So you can, and sometimes there's some switches that you can't get into, like these switches. You could get a dirty contacts, but you can't open the switch, but you can spray the contact cleaner in through here or in through here, and you move the switch back and forth, and it self cleans. So that's the contact cleaner comes in a spray can with a long skinny nozzle, and you can use those for rotary switches. So a lot of audio equipment, the switches, the dials, and get dirty, the contacts, so you can spray inside and just turn the dial or switch the switch over a few times and it cleans it.
A question here, if you do not have exactly the same switch, but you have others that are another value, can you use a higher value switch without danger, as you mentioned?
Yes, as long as
or a lower value.
The current rating has to be greater. So here it's 5 amps, 120 volts. So I would, if you have a 10 amp switch, that's fine. If you have a 3 amp or 4 amp, no good. So you have to overrate, always overrate if you can. There's some things where you have to have the exact right current matching, but most things, like for instance, your adapters for your computers, as long as you have more current rating, you're okay. I'm just trying to think. Fuses. Never overrate a fuse, because the whole principle of a fuse is that it's going to blow. You want it to fail, right? So when you get a fuse like this, you can't overrate it or underrate it. You have to get the exact right value, because if you underrate it, it's just going to blow all the time. This is meant to fail above 3.15 amps, but 3.15 amps is what it's going to use. So if you put a 2 amp fuse in here, it's going to blow. But if you put a 4 amp fuse, it won't blow, but it's supposed to. So fuses have to be exactly the rating that you see on the fuse, not above or below.
Thank you, Paul. I'm just aware it is 2:30.
Okay.
So how many more minutes do you think you have of your presentation, if people can?
Well, I think everything now is,
any key
this I was just going to mention, but I didn't really go into too much into heating elements as another common failure mechanism. It's basically a wire that just breaks. Normally the connections break, or somewhere in here the wire breaks. Relays get dirty and they need to be cleaned because they're switching all the time. You can see in this case, you can actually take a cover off and clean. There's your connections right there. Some relays are potted. That means they're not meant to be open. Then you have to replace them. With relays, again, you have to match the specifications. Heating elements are very hard to replace. In most cases, they're custom designed. And if a heating element fails in most everything, you can't fix it. It's the end of the line. Rechargeable batteries are another common problem. They don't last forever. Rechargeable batteries stop recharging eventually. So you have to replace them, and that hopefully you can buy. This is opening up to show you, but hopefully you can buy the whole package, like in a drill or something. But be very careful when you're buying cordless tools, because if eventually they stop making the batteries, and then they're useless. Motors, they're more complicated. Besides the fuse, there's different mechanisms. I'm not really going to go into it too much, but one of the common problems are these brushes which connect the power to this thing called a commutator. They can be cleaned. They're meant to be replaced, so they're usually easy to take out. They can actually be cleaned. The problem with them is, you see, they're spring loaded. If they're not moving back and forth, then they don't work. So they have to be free. And these things get dirty, and then they get stuck in their little slots. But that's pretty advanced repairs. So let's see, I think that's pretty much it.
Okay. I'm going to thank you, Paul. I'm going to just pause the recording here, and so I can make some announcements and then some questions after that. So I'm just